Welcome back everyone. This video is really a continuation of the last video. We're still focusing on energy for the most part. We are going to apply it to things that are rolling. Think of like a bowling ball going down the lane of a bowling alley, or like you take a tin can and you roll it down a hill. So things that are rolling across a surface. And not only are we going to look at energy and some good conceptual examples, but we're kind of going to preface this by looking at what's causing this rotation. We're going to go back to looking at forces and torques so we understand where this rolling is even coming from. Okay, so I have this scenario here, and we're going to look at those forces and torques, but before I want to point out two terms. And two of these terms are things that you're going to see pretty often in the future. You may have actually seen these before in some of my homework assignments, but it's worth knowing so you don't get confused or think that something weird is up. The first term that you often see is this thing that says rolling without slipping. And what that simply means is when we're looking at rolling objects, scenarios where things are rolling, I have this roll of duct tape right here, we're assuming it's kind of nice, smooth, easy rolling, like it's going like this. We're not imagining a scenario where like you're in a car and like you slam on the brakes and so the wheels are just sliding, right? They're just grinding across the pavement. That's not rolling without slipping. It's slipping, so to speak. Okay. We're also not imagining like a car where you just slam on the gas and then the wheels are spinning out from under the car. We're assuming nice uniform rolling so that when the object is rotating, it's also translating in a way that matches. Okay, and also we have this term rigid objects. That just means we're looking at things that are solid. They're not bending, they're not warping, because that, of course, would just make our physics a little bit more complicated. Okay, so with that said, here I have, let's say it's a solid disk. I'm letting it go from rest, and we want to figure out what's causing it to start rolling in the first place. Now, to be honest, this is not really a full-fledged proof I'm doing right now. I'm kind of skipping some details. To really prove it, like if you wanted a math proof, you would need to look at a couple different axes of rotations, and you would need something in physics called the parallel axes theorem, both of which are beyond the scope what we need in this class. But I want to say this in advance because I'm not saying anything wrong, but if you happen to crack open a textbook or you do a little more digging in what is an interesting topic, you might get a little bit more info than what I'm going over right now. But to get our point across, let's think of this disk, let's think of this object, and we're going to focus the hinge, the rotation point, about the object's center, which makes sense because if this is a rolling can or a spinning wheel or something, it is in fact rotating about its center. That's definitely true. So if this is our hinge right here, let's think about the forces that are going to act on this disk. Well, I know that there's weight acting on it. Let's see, let me change colors. I'm going to go here to red. I know there's weight, and we know that weight acts at the center of mass, and it goes straight down like that. There's mg. Is weight applying a torque on this object? Oh man, my arrow disappeared. No, because this weight is acting right where our hinge is located. We learned this already. If the force is acting where the hinge is, there's no distance, therefore there's no torque. So it's not the weight that's making it rotate about the center. What about the normal force? Well, if I was to draw the normal force, remember the normal force is coming from contact between the object and the surface. So it's coming from this point right here, and it's going to be acting, of course, perpendicular. And I have this white dashed line because I know I can't draw very well. That normal force should be acting like this, kind of through the center of the object, perpendicular like so. Okay? Is the normal force applying a torque? No, because the normal force is also passing right through the center. Neither the normal force nor the weight of the object are applying a torque. So neither of those two things are making it rotate. And boy, that's really a problem, because if you imagine the can or the ball or whatever at the bottom, is it rolling? Is it rotating about its center? Sure, it's definitely rotating. So there has to be something that's causing this rotation. What do you think it is? What force could be applying a torque to get it to rotate? It turns out it's a frictional force. There's friction acting on my object that's causing it to rotate. Because remember, friction is acting between the surface, and that means it's going to be some r away, and it's always acting parallel. So it's either going to be up the ramp or down the ramp. So if this object is rolling down the ramp, what direction is the frictional force going to be? If it's a little confusing, let's think again back here. Notice what the object's doing. It's rotating this way. It's rotating clockwise. So if it started at rest and now it's rotating clockwise, well, there has to be a torque that's making it rotate clockwise. And therefore, the force must be in the direction that would cause a clockwise torque. So if I go back here, would I need a force going up the ramp, so to speak, or down the ramp to cause a clockwise torque? It would have to be acting up the ramp. And that's a little unintuitive because obviously this object is rolling down the ramp, but friction is acting up the ramp. That's what you need in order to get it to start rotating in the direction that we want. So let me get rid of this right here. A little add on to our notes. The only force that can make it rotate is friction, and in this case, friction is pointing up. I'll put it like this. This turns out to be a static friction, and I'll prove it a little better later on. I kind of like to think of this as like a stone that's on the ground. When you walk by, maybe you trip over something. Okay, the friction is what's kind of snagging. It's kind of holding this point down that allows it to pivot and continue to go in that rotational kind of motion. It's a static friction that's going on. If you don't really trust me that it's static friction, an animation we're going to see in a second is going to help. If you don't trust my poor drawing abilities, here's maybe a more well-known, a better made diagram. But again, it's showing all the same thing. If this thing starts rolling down the incline, well, the normal force isn't applying a torque about the center. The weight's not applying a torque about the center. It's a frictional force that's opposing a torque. There's no other forces that are acting on this object. And that friction has to be acting upwards because I need a torque that's going to make it rotate, in this scenario, clockwise. Okay. Well, okay, so in that scenario, when it started at the ramp and it was rolling down, friction was acting up the ramp. Well, now let's think of another scenario. Okay, now let's think of it like this. Now I have that ball. It's almost like a continuation. Now the ball's rolling across the surface, and now it's going to roll to the top of another incline. So it's rolling here, and then when it gets to the top, it's at rest. So it's no longer translating. It's no longer translating like this. It's no longer rotating. If it's no longer rotating, it must be slowing down, right? The rotation must be decreasing. So that means it has some rotational acceleration or a deceleration, if you will. It's still going to be a frictional force that's causing it to slow down rotationally because the normal force is still acting in a way that's not applying a torque relative to the center hinge. Neither is weight. What direction is the friction going to act so it slows down on the way up? It is also up the ramp. Oh man, and that's weird. In both scenarios, the frictional force is acting up the ramp. If that's confusing, think of it like this. It was rotating clockwise. So if it's slowing down, it must be rotating less and less and less clockwise. Well, if I'm slowing down in the clockwise direction, the acceleration, the angular acceleration, must be counterclockwise. And that means I must have a torque counterclockwise. So if I need to get a counterclockwise torque, I need a force that's going to act in that direction. Oh, this is weird. Remember what I said before? Rolling is complex. It's unintuitive in many ways. I needed a friction kind of pointing up the ramp just to get it rolling because I needed a frictional force in the same direction that it was speeding up. Same thing is true here. I need a frictional force that's going to point in the right direction that now is causing a torque that's in the opposite direction of its rolling. And in both of these cases, it turns out that that's up the ramp, from the bottom part to the top. I should go like this to match my diagram. Now, with that said, is there still conservation of energy if there's friction? And it turns out that, yes, there is in fact still conservation of energy even if there's friction. I'll show you a really good reason why in a second, but we're still kind of taking into account any possible work that's being done with this, right? We're looking at this rotational kinetic energy, 1/2 I omega squared. So if you're worried about like forces and work and non-conservative, we don't have to, because we're accounting for this rotation when we're using our rotational kinetic energy formula. Okay, now part 5, okay. Slide 5. I don't know why I said part 5. That doesn't mean anything to you. I have an object that's now rolling on a flat surface. Is there a frictional force now? This is a common question I get. Is there a frictional force if it's rolling on a flat surface? The answer is no. And it's no for a couple reasons. One, we can kind of prove it by contradiction. If there was friction acting this way, well, that would apply a torque going this way, and that would make the ball slow down. And that's not happening. It says it's moving at a constant speed. If instead we said there was friction going this way, well, that would mean there's a torque this way, and that should make it speed up. Oh, okay. You do not, in fact, need friction to have something rolling. And again, think of like a bowling alley. I know a bowling alley isn't perfectly frictionless, but they really wax that surface of the lane. You don't actually need friction to have something rolling. You could maybe even prove it to yourself with Newton's first law. I have an animation that shows you why friction is not needed and not required. So I have my rolling object, and that red dot, that's tracing a point on the rolling object. And this arrow that you see, and it's going to reset by itself, this arrow, that's showing a relative velocity of this dot. And here's what's important. Okay, this is like tracing out the motion of that point. And obviously, as it's rolling, we can see that it's traveling to the right, of course. But notice what happens when this point is making contact with the ground. It has zero relative motion. Let me pause it right here. Ooh, right when it touches the surface, that point is not moving relative to the surface. And remember what friction is. Friction opposes sliding motion. It opposes motion like this. But when it's rolling, that point is no longer moving relative to the surface. There is no sliding that's taking place. No sliding taking place, no friction. So in fact, energy is still conserved because whatever this friction that's going on that is in fact present, it's not doing work. There's no displacement going on. Okay, there's no friction required when you're on a flat surface because there's no relative motion when that spot of the disk is actually making contact. Now, this does in fact break down if this was a warped object or if there was that slipping going on. That's why we mentioned that at the beginning. Okay, so energy is still conserved. No work, no non-conservative work is being done by friction. So we can still use conservation of energy. And we don't need friction when something is rolling on a flat surface. Now, I like this picture just real quick. In real life, things warp. This is pretty dramatic, but even in real life, something that seems pretty solid warps slightly when it's on a surface. And therefore, that means it kind of spreads out. There's multiple forces. If you could look here, you can maybe imagine that there's not going to be a nice canceling of just one overall normal force. This is a reason why things slow down when they're rolling in real life, so to speak. Now, with that said, oh my gosh, I spent a lot of time talking about just the rolling aspect. Let's look at the energy. Okay, let's look at the energy of two things that are rolling. So I have scenarios. This is really just going to take the form of two example problems. In this scenario, I have a disk, kind of like before, and we're going to say it's rolling without slipping. There is, in fact, friction on this incline because we need friction to get it to start rolling, okay, to apply that torque to get it to rotate. But right next to it, imagine I have like a block of ice, and it's on a frictionless surface. So the block is going to be able to slide down without slipping, without rolling. Okay, and there's no friction. It is able to slip, I should say. The wheel is able to rotate, and it's able to roll nice and evenly, all right, in the way that we saw before. All right, now, which of these two objects is going to get to the end first? Which wins the race? Which gets to the bottom first? What do you think? I have an animation that I want to show you. I have this set up. So let's reset right like this. Let's go and reset. Ooh, I'm having some technical difficulties. Just a second. Here I have my scenario. Let's run the race and see which one gets to the bottom first. Let me move this a little bit like that so you can see it. Okay, and they're off. Let's see, here we go. Which one's gonna win? And oh, it was the sliding block. Let's reset. I mean, of course, it's an animation, but good science is doing multiple trials. The sliding block gets to the bottom faster. Why is that the case? Why is it that the sliding block is going to get to the bottom faster? Let's look at the energies of these two things. For the block, we have potential energy turning into good old kinetic energy at the bottom. So we have at the top, we have at the bottom. The block is never rotating, so all that gravitational potential is turning into translational kinetic energy. Well, let's think of the rolling disk. So I'm going to put disk. It says here that they have the same mass, okay? So they're going to have the same gravitational potential energy. Both objects have the same total energy in the beginning. And in fact, both need to have the same total energy at the end because energy is conserved for both of them. But this is the key idea. When we're thinking about which one wins the race, we're really trying to argue which one's going to be going faster, right? Because if they're traveling the same distance and one gets to the bottom before the other, it gets there at a shorter time, it must be traveling with a greater translational velocity. So which of these two has a greater translational velocity? It's going to be the block, because the disk has to convert some energy not just into translating, not just into going down the ramp, but also to rolling, to rotating. So because they have the same energy in the beginning and the rolling object uses up, it consumes, so to speak, some energy to roll, it's going to have less energy available to rotate. This is what I would write down. Things that don't have to rotate will often win the race, so to speak, because they don't have to spend any energy to get rotating to begin with. So if I have a comparison between an object that does rotate and one that doesn't rotate, especially if the scenario is like this, the one that doesn't need to rotate is going to have more kinetic translational energy at the bottom, therefore it's going to have more speed at the bottom, if all else is staying equal. Okay, I have one more example for you. Okay, one more. So I have another scenario, very similar. I have this ramp here, I have that disk again, but now I don't have the block. I have a solid disk and I have a hollow hoop, kind of like my duct tape. Which one is going to win this race? And I'm telling you, they're going to have the same mass, and let's say they have the same radius. Which is going to reach the bottom? Take a second. If you want, hit pause on this video. Try and reason it out. Which one, if either, is going to win the race? Let's try it. Again, I have my animation. Now I can reset it here. So I'm going to hit reset. I'm going to get rid of the block, and I'm going to get the hoop. Let's see which one wins the race. You can test your prediction. The solid disk wins the race. Once again, let's watch. They start at the same spot. They both start at rest, the same potential energy. Now both are rolling, but the solid disk wins. Why is that the case? Why is the solid disk going to win in this situation? First of all, let's see if you fell for a rookie move. I said they have the same mass. I had them with the same radius. Does that mean they have the same rotational inertia? Is that true? No. They have different rotational inertias. Which one has more rotational inertia? The hoop does. Maybe I should do this in blue. The blue hoop has more rotational inertia because it has, even though the same total mass, it has more of that mass farther away. So one of these objects has more rotational inertia than the other. And it turns out that's what determines which one wins the race. I'm going to save us a little bit of time, and I already wrote out a derivation showing the conservation of energy. So for both objects, they both start out with just gravitational potential energy. Okay, so both have mgh, and they're the same mass, so this term is the same for both. Both end up translating, and both end up rolling. So this is the same term for both. Okay, I don't know what happened right here. This should be I like this. I don't know why I have that little mark right there. Let's see, can I get rid of that? Make that nice and neat. Perfect. Okay, so if we look at this scenario, and to be honest, we have a couple terms that we don't want to deal with individually. We have V and omega. Remember, there is a relationship. V equals omega times R. Let me delete that. Oh man, wasting time. V is equal to R omega. Therefore, omega is equal to V over R. So that's what I plugged in right here. So now my terms, I just have V, I have H. H is the same for both. We're trying to compare their V values. And then there's I. And they have different rotational inertias. Look at this equation here at the bottom. Okay? If one of the objects has more I, more rotational inertia, that means it's using up more energy to rotate. This term right here, the rotational kinetic energy, is bigger for things that have more rotational inertia. And therefore, if more energy is going into rolling, well, there's less energy available to translate. Remember, they both had the same starting energy. So if they both have the same starting energy and the hoop requires more energy to start rolling or to roll, it's going to have less energy to actually go down the incline. So it's okay that I actually didn't give you the equation on here. Maybe that's what you thought. You're like, wait a minute, Thrasher, you didn't give us the two equations. If you know that they have the same radius and the same mass, and in fact, if you actually do a little bit more of a derivation, the mass and the radius actually even cancels out in this equation. But if you can prove which one has more rotational inertia conceptually, like what we just did right here, we conceptually proved which one has more rotational inertia. Well, that means it's going to use up more energy to rotate. So using energy for these types of problems for rolling objects, it's important that you think about rotational inertia, because that's usually going to affect your final answer. And again, as we said before, something that doesn't need to rotate, well, you don't need to use up any of your energy right here. So that can affect what's going on in terms of like winning a race or traveling the fastest down at some certain point. Oh my gosh. A long video, I know, but that's the last bit of rolling physics, both the mechanics, the physics in terms of torque and forces, as well as the energy that's associated with it. Thanks a lot for watching.